Are there any questions that anybody would like to ask based on the material we've been doing?
Can we go over 5.2, number 3?
Number 2?
Number 3?
3, okay. Say 5.2?
Yeah.
Okay. Here's an interesting one from a little bit back then. And it says this, suppose you look at this region, it's got the line y equals 3 minus 2x. And you're going to revolve this around the y-axis. And it says find the volume of the solid if you revolve it up to 2 here, and wherever it intersects over here. You get something like that. The volume. Come up the first test, you can use different methods on this. I think either the method of cylinders or the method of discs will work. What you do on this one is you notice when you revolve around the y-axis that if you take a cross-section, the cross-sections are washers, right? There's no hole in the middle, perpendicular to the y-axis. So the volume formula using the method of discs for this one would be the integral, y going from its minimum value here at 0 to its maximum value at 2, of pi times the radius. And you take the typical radius at y, you take the disk at an arbitrary point y, and say, what is x equals f of y at that point? Well, it's to the line. I have to rewrite this, x is a function of y, so I'll rewrite that as y minus 3 equals minus 2x. Equivalently, x equals y minus 3 over minus 2, or you might write that as x equals 3 over minus 2. 3 minus y over plus 2. Let's do that. So f of y is going to be 3 minus y over 2. And that's what the integral is. It's pi times the radius f of y squared dy. And it's just a special case of the cross-sections method. This is your area A of y. You integrate the cross-sectional area from the beginning of the cross-sections to the end. That's what disk is, a special case of the cross-sections method. So I'll write that as the integral from 0 to 2, pi times 3 minus y over 2 squared dy. I'll let you do that one.
Did you change it into x equals 3 minus y over 2 because instead of it going from A to B, it's going to C to D?
Yeah, exactly. Yeah, if the cross sections are perpendicular to the y-axis, then you want to integrate y going from C to D, where the cross sections begin to where the cross sections end. Exactly. Yeah. Anything else you'd like to see? Just a reminder, real quick. On Monday we have Labor Day, so there's no class. Not too long after that, I think we come up to our first test. So be thinking over this week while you're on of the more questions you want to ask. Well, we will finish the chapter shortly. The first test may be on this chapter we're finishing tonight, or maybe it'll be a little past. We'll see. But no class on Monday.
So the test might be Wednesday? Or?
No, it's on the syllabus. I don't think I brought the syllabus. I've forgotten what it is. I think it's the following week, not next week. I think it's next week. They're early because I need to keep them up. They get more testing. You might week or two after next.
Look at 5.6, number 5.
Okay. All right, 5.6, number 5 says you have a constant force of 10 pounds, LB or LBS, is in the positive x direction. Is applied to a particle whose velocity versus time curve is as follows. This is a tricky question, isn't it? Here's the time t, here's the velocity v, and it goes up something like this. And if you look at the graph, it looks like it goes through the point 5 here and 4 here. So it's a velocity 4 after 5 seconds. Goes right through that point. Looks like a straight line. Picture. Find the work done by the force on the particle from t equals 0 to t equals 5. This is good because we mentioned we could do this one, but we really didn't do one quite like this. This is a little bit like the wagon problem. I guess it's pretty good. I like it. Find the work done by this force. Along the given path. From t equals 0 to t equals 5, they say. All right. It's a constant force. For a constant force, we say that the work is simply force times displacement. Distance, if it's positive, you can say. What's the force? The force is 10 pounds. What's the displacement? Well, you just have to say, suppose it starts from 0. If this is velocity, velocity is, if it's moving in one dimension, dx dt. And so the displacement x is the integral of the velocity dx dt. dt. When you integrate this, you get x. Going from t equals 0 to t equals 5. What is dx dt? It looks like it's a line of constant slope. Y is a 4 over run of 5. So this is y equals 4/5 t, or I guess b equals 4/5 t. And so this is the integral from 0 to 5, 4/5 t dt. Integral of 4/5 t, the 4/5 comes out, and t integrates to t squared over 2. So you get 4t squared over 2, plug in 0 and 5, gives you 2t squared at 5 and 0 is 50. This was in feet per second, was it? Yeah, feet per second, they say. So this would be feet. Now I'll say force 10 times distance 50 gives me 500. It was in feet and pounds, so it's foot pounds. That's actually kind of a hard problem, but it's supposed to get used to. Just a simple case, a constant force, it's force times distance is the word.
I was just confused on how to find the displacement,
Yeah.
which is the,
Yeah. We go by, if they give you velocity, integrate the velocity displacement. Okay, anything else? Hey, tonight we got moments of mass on the theorem of Pappus. And it comes with a little bit of physics in it. Suppose you balance a bunch of masses here. M1, 1, M2. They might be different weights, not necessarily all the same weight. Mn, n different masses, and you put each of them at a position x1, x2, xn. I'm going to do a shorter treatment than the book does. When I look at that, it just confuses me. There's so much notation in there. Maybe I'll make you feel better when you read it. I just like to do this about the point x equals 0. Somewhere along here, there's the point x equals 0. And rather than doing it in general with a fulcrum or something placed anywhere along here, if you place a fulcrum here and you say, what's the moment of mass for this kind of teeter-totter thing about x equals 0, if this is the x-axis, and you assume these masses are all sitting on a massless rod here, what do they tend to do to this? They can tip it one way or another depending on the torque that's applied. The force times the distance gives you the torque. So a mass that's twice as far away as another mass of the same weight will exert twice the force because it's twice the torque because it's twice as far away. Two masses at the same point, the larger mass it exerts twice the torque because it's twice as heavy. But that torque is just proportional to these moments, and we'll just say the moment, just to be simple. That's what the book does. The moment of mass, they do it about an arbitrary point. Let's just say the moment of mass about x equals 0 is simple. It's just the m1 x1 plus m2 x2 plus dot 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 mn xn. Then if you multiply this by the force of gravity, you actually get the torque. Right? The gravity times the mass gives you the force, and then times the distance is force times distance is torque. So this will give you the, if you multiply it by gravity, you'll get the torque, the tendency to this thing to try and turn. Now when x is negative here, it's exerting a negative torque, turning it this way. When x is positive torque that way, if you count that as positive turn. Sometimes people like to do counterclockwise, it would be the opposite. But we'll say this is the moment of mass, is this. And then the center of mass is found by, oh, by the way, this also has a summation notation. You could say sum, right? Sigmas per sum, k equals 1 to n, the number of masses, mk xk. So that's the sigma notation for it, capital letters, sigma for sum. This means this. The center of mass then is usually denoted x bar. It's the average point of mass. It turns out to be the balancing point where you can put your finger and it wouldn't torque either direction. You could balance it right there. Is the moment of mass, sum mk xk divided by the mass, which is the sum of all masses. K equals 1 to m n mk. So there's the center of mass for that group of little masses, the balancing point. This is an important point actually in physics, if you've ever seen what it does. If I take some oblong object, maybe a bowling pin or something, right? And I throw it, what path does it take, ignoring air friction? If I were to take the center of mass of this thing it would follow a nice parabola. It treats in constant gravitational field, it would follow as a parabola. Maybe it's spinning as it goes along, so it looks like this, it spins around, but the center of mass travels a nice parabola in constant gravity. Every other point does something different, like this point up here that's not the center of mass, it goes like this around the center. But the center of mass is kind of an important point because it's where you can do an easy calculation of the trajectory. All right, so that's the calculation. Now the question is, what can we do with that with calculus? For a continuous object, let's say a rod of varying density, the book doesn't do varying density, though they do varying height. So I'll just do it the way they wrote it out. Let's say a constant density delta, just to follow the book. And height, f of x at x, what is the center of mass? So I have something like this maybe. Here's y equals f of x. It's made out of a uniform material, constant density, and it sits along the x-axis. And I would like to place a fulcrum under here, make it balance, right? Where can I balance it? Where's the balancing point x bar for that? You can kind of guess. You can break this up into little rectangles, right? And think of these as little rectangles as little masses, right? And you could say that x bar, by the formula we have over here, x bar ought to be approximated as the sum of mass times x. Well, what's the mass times that? Times x. The mass of each little thing, if you take the kth one here, it's got a width delta xk. It's got some height at any point you want to take it inside. Let's say the height of this rectangle I make to be f at xk star, some intermediate point on the kth interval. So on the kth interval, you've got a base, delta xk, the base, times the height, which is f of xk star. That's how high you make the rectangle. This is the area of the rectangle. So how do I get the mass from the area? Just multiply it by the density, right? If you multiply 2 kilograms per square meter times the number of square meters, you get the number of kilograms. So you multiply by delta the density. So density delta times the area of the little rectangle gives you the mass of the kth piece. So this is the kth mass. And then I have to multiply it by xk. xk star, let's say, just use the same point. And sum that k equals 1 to n. And that's exactly this formula applied to these little rectangular weights, each is the same density delta. It's like you stacked a whole bunch of little bricks on top of here, all of the same density. Nice. And then you divide that by the total mass. What's the total mass? It was just this part without the xk star, right? We took mass times position. So this will be just sum k equals 1 to n delta f of xk star delta xk. By the way, you hear delta, delta. This is a small delta. This is a capital delta, even though I draw it smaller. So that's why they look different. This capital delta, this small letter delta. We use a small delta for density, a big density for the increment. And now what have I got? In the limit, as n goes to infinity, we notice that all these approach the same number regardless of the partition and the point we pick on the partition, as long as f of x is continuous. So for a continuous f of x, that limit is what we ought to call the mass on the bottom and the moment of mass on the top. What we get is that x bar equals the limit of those, sum delta times f of xk star delta xk star over the limit n goes to infinity of everything but the xk star. Now what have I got for that formula? X bar equals what? Maybe I need to erase this. I hate to do it. The limit of the sum is whatever function of xk star you have here, you just put x instead, and then the delta x becomes a dx, right? This becomes the integral from the beginning to the end, a to b, if this goes from here x equals a to here x equals b. And so this becomes the integral from a to b, the limit of sum. The delta xk becomes the dx, and this is just notation for this, right? And then you put f delta f of x, you replace the xk star with x, times x. And on the bottom, what do we have? We have everything except for the x. So on the bottom, what you get is the integral from a to b, delta f of x dx. And it's just like you did here. This was the moment of the mass for the discrete case where you have n masses. And you divided it by the total mass to get the balancing point. You can show mathematically that that's where it will balance it. Work thing I was telling you about. We don't need to do that here. But what is this then? This is the exact same thing for the continuous case. Now you have a continuous thing instead of a bunch of discrete masses. And it has a balancing point by taking the limit of the sum, treating this as n individual masses. You get this formula. And the top one, again, is the moment of mass, and the bottom one is again the mass. We can call this equation 2. I call the other one 1. This will be equation 2. Oops. This will be 2. Sorry. All right, so here's the discrete mass, center of mass, moment divided by mass. Here's the continuous case. Moment of mass divided by mass is the center of mass. And now we have the calculus of this stuff. We can do this for continuous objects of constant density. I do want to mention one more thing. What I don't like about this presentation is they assume constant density delta. You don't have to assume that. You can make delta a function of x and this formula still works. So delta in general can be a function of x, but they didn't write that. Now that we have that, we can do some problems with these, calculating center of mass for various objects. Here's a simple problem, the first one. Let's do the discrete case first. This is number 1. Suppose I put these three masses here at x equals 0, x equals 5, and x equals 10. Here I put a 5-pound mass. Here I put a 10-pound mass. And here I put a 20-pound mass. They do two things. They put part A for the fulcrum at 5. Is the moment of mass positive, negative, or 0? This is not the right moment. This is the moment about x equals 0. Let's say the moment about x equals 5, which corresponds to this one, then you have to replace xk by xk minus 5. Positive, negative, or 0. Well, we'll say for that, the moment of mass is the same formula you have there, except with x replaced by x minus 5. Let's sum mk x minus xk minus 5, k equals 1 to 3. That's the top of the moment in 1 about x equals 5 this time instead of about x equals 0. Just have to put x minus 5 instead of x. And this is, the first mass is 5. Well, they said without calculating it, didn't they? Which should it be? Should it be positive, negative, or 0? So without summing. The moment of mass, remember, if you multiply it by gravity, it's supposed to give you the total torque. It's got a, if you put the fulcrum here, it's got a big mass on this side and a little mass on this side. It has to be tilted this way by the big one. It has to be positive. So positive because the big mass is on the right. More moment to the right. These are the same distance apart. This one's 4 times as heavy at the same distance. It's going to turn it this way. More weight at the same distance to the right. And then part B says, where shall the fulcrum be placed so that the beam is in equilibrium? Here we can just use formula 1. Find equilibrium position, x bar. Now we don't need to take the moment on x equals 5. We can just use formula 1 directly. By formula 1, x bar is the sum of the mk's xk. So we'll take m1 x1 plus m2 x2 plus m3 x3. I'll drop that sigma notation over the sum of the masses, m1 plus m2 plus m3. So we've got 5 times 0, right? Weight times position plus weight times position, 10 times 5 plus weight times position, 20 times 10. There's the moment of mass about 0, is that, over the sum of the masses, 5 plus 10 plus 20. And if I calculate that, that will tell me the balancing point or the equilibrium point is, let's see, 0 plus 50 plus 200 is 250 over 35. Let's see, this is 57ths, huh? 7 1/7, if you like. So balance is somewhere over here at 57ths. You'd expect it to be over here, right? So when the bigger weight is close to the fulcrum and the 5 is way out, the small weight can balance the big weight just like on a teeter-totter, right? The torque on each side is the force times the distance. This one's bigger distance, this one's bigger force, and then balance. Bigger weight and bigger distance to balance.
When it says moment, I think I'm having a hard time kind of conceptualizing that. Does it mean like its position, like where we're looking at, or what exactly does moment mean?
Yeah, if you multiply the moment times the force of gravity, then it gives you the torque, which is the tendency of it to turn. That's the concept. I don't know how to describe it very well beyond that.
What did you say just a second ago? How did you describe it?
If you multiply the moment of mass times the force of gravity, it gives you the torque,
Okay.
which is its tendency to try and turn about the position. So there's the discrete case. It's just using Formula 1. Now let's try a continuous case with Formula 2. Now they call this the center of gravity instead of the center of mass. I wrote this author many years ago and he never responded, maybe never paid attention to it, but technically it's wrong in here. For such a tried and true book, I'm amazed they don't fix this, but center of gravity and center of mass can be different. In a uniform gravity field, center of mass and center of mass are the same. And that's all the kinds of problems they put in here. So for this particular application where it's constant gravity, yes, they are the same. It's not wrong. But the terminology is wrong if you apply it to a non-constant force situation in general. But we'll do this one. Find, I'll reword it. Find center of mass, find the mass and center of mass. If now you have a continuous object instead of discrete objects, if you lamina, that means a flat plane region, an object that's so thin and flat you can treat it as a plane region, is bounded by the x-axis line x equals 1 and the curve y equals square root of x with density delta equals 2. What I don't like about this section is when density is constant, all the formulas, it doesn't matter what density is, you always get the same answer. But they're trying to keep it simple. Now we need Formula 2. First, the mass, I wrote it on the bottom of Formula 2, so we'll say denominator of Formula 2. The mass is just the integral from a to b of delta times f of x dx. This is integrating the density at each x over the length of lamina. And so this is the integral from, let's see, it helps to draw the picture, doesn't it? Well, y equals square root of x is this half parabola here from x equals y squared. There's y equals square root of x. I want to bound it by x equals 1 about here. And the x-axis here, y equals 0. So there is the thing I'm interested in finding the mass and center of mass of. It looks like it goes from x equals 0 to x equals 1 here. So that's my integration. integration limits. Delta, the density of this, whatever it is, piece of metal or something, is 2, whatever, kilograms per square meter or something like that. And then f of x is the height of the thing. We're thinking of making little rectangles and then taking the limit of stuff. So f of x is square root of x dx. I just have that. So it's the height times the density per square area gives you the density per unit along the x-axis times dx, or integrated with respect to x. So I have integral of x to the 1/2 is x to the 3/2 over 3/2, or I'll write that as 2/3 x to the 3/2. Plug in 0 and 1. This looks like 4/3 times 1 minus 4/3 times 0. It just comes out to be 4/3. Now, they tell us what the units were on this thing, I don't think.
So why would you only take the denominator of the?
Because the formula was for the center of mass, x bar, was the moment of mass divided by the mass. So the denominator was the mass. The reason it's the mass, you go back to that diagram. You have y equals f of x, and you integrate from a to b. You're thinking of adding up all these rectangles, and what's the mass of each rectangle? It's the sum of the density times the height. This is density per square unit, times delta x, and then when you take the limit of that, it's integral of delta f of x dx. So it's adding up all these rectangle masses and taking the limit as number of rectangles goes to infinity, gives integral delta f of x dx. So it was that rectangle formula we did. Mass is equal to this, but that was the denominator in x bar. But you take, if delta is a density per square unit, then delta times the area of a rectangle gives you the mass, right? Density, whatever, kilograms per square meter times square meters gives you kilograms. And then if you sum that's the kilograms of the kth piece, and then you sum all n of them, you got the sum of the n rectangles, then you take the limit, you get the actual mass of the object. All right, so there's that one. And that's what was in the denominator with this. So the mass is 4/3. Now we need x bar, the center of mass. That would be the moment of mass on the top, which is the same integral, just stick x in it. X bar is the integral delta f of x dx from a to b over the integral from a to b delta f of x dx. But this one we know we already calculated was 4/3 mass. The top one is the moment of mass. That's what we need to calculate still. I just erased it, but the region went from x equals 0 to x equals 1. The density was 2. The height of the function was square root of x, and then I need to multiply that by x this time, dx. And the bottom I can just put in 4/3 and recalculate. So integral x to the 3/2, right? Twice the integral x to the 3/2 dx from 0 to 1 over 4/3. X to the 3/2 integrated gives me x to the 5/2 times 2/5. I need to plug in 0 and 1. Well, this just gives me 4/5. So I have 4/5 divided by 4/3, 2 fractions. This gives me top times bottom over middle times middle, gives me 3/5. So the balancing point of this is 3/5. I suggest when you're done with these, always look at the picture and see if it looks right. It's so easy to do this real calculation and make a mistake. Does this look like the balancing point? I take y equals square root of x, a half parabola, but I only take it out to x equals 1. Does it look like it would balance about 0.6? Yeah, that looks reasonable. It's a little higher at this end, a little longer at this end. It looks like it could. And that's so that should be right, we think, by visual inspection.
You said X bar, what is that?
Yeah, X bar. That's just the notation I like to use. It's the average position of mass. It's really what it is. If you take a statistics class, you can do these same kinds of calculations. Like if you have a frequency distribution and F sub k people get a certain score and their score is xk, and xk is the number of people getting that score in the kth group. I'm sorry, no, fk is the number of people and xk is the score. And then you divide by the number of people, the sum of the frequencies. This gives you actually x bar, the average score. So this is like adding up all the scores. Frequency times number of people is the sum of all the scores. Divided by the number of people is add up all their scores, divided by the number of people, that's the average score. So this is actually exactly the same thing, just adding up the mass, finding the average mass point. The mean point. And they also use X bar in statistics for the mean in a lot of the calculations. Yeah, there's nice analogies if you can draw them and you can remember this one. All right, that's it on that section. On that topic. There's one more topic in the section, and that's the theorem of Pappus. So this one's a little easier. If you want to do another problem of that, we can. I consider that one of the less important topics because it's not really any new calculus. It's trying to get you in the mode of thinking, how can I apply calculus to problems where I have to break up the problem into little pieces and take limits of sums. So it's giving you that practice. We did the swimming pool, we break it up into layers. We do this one where we break it up into little rectangles. And you see those kind of things, you get a feeling for how to do these applied problems, but the problem itself is not so important unless maybe you're going to be doing these physics problems, then you want to learn it better. Here's the theorem of Pappus. This one's a little more, oh, I'm sorry, I forgot to put one more thing. Very important, actually, for the mathematician. Note, if delta equals 1, then what does 2 become? Suppose I have density 1. We get x bar equals just the integral of f of x times x dx from a to b over the integral from a to b of f of x dx, right? You just take the delta out of there, and otherwise it's the same thing. This one we'll call 3. Is called the centroid. Almost forgot to write this for a second. Of the plane region that you're integrating over. You're integrating f from a to b, so it's the plane region from a to b over the x-axis and below the curve y equals f of x. The centroid of such a plane region has this formula. So maybe we should do one of the centroid problems. However, once you see it, you say, wait a minute, it's the same thing. You know why it's the same thing? This is what I don't like about this silly section, trying to make it so easy they assumed constant density. What was the other form compared to this one? All you did was add density in here, right? Delta and density in here, delta. This was the formula for center of mass. Take the delta out, and it's the formula for centroid. What's the difference? If it's constant density, which every single problem in there is, then you can pull it out of the each integral and cancel it, and you get the same number. So that's what I don't like about the section is actually if you only allow constant density, and then the centroid is always the center of mass. So here's one of the significance of the centroid is the center of mass for an object of uniform density. If density is constant, delta, you can pull it out and cancel it, and it's the same. All you have to do is calculate the centroid. There's one significance of the centroid. I like to think of it as the center of the area. But it's ever called that in a textbook, but that's really what it is. It's the mean point of the area that you have. And so the book is right, there is a difference, but only if delta is a function of x. If the density varies along the x-axis, delta of x, then you can't pull it out of the integral and calculate it, and it won't be the same if you do center of mass and centroid. Well, we'll just say this is the formula for centroid, and when delta is constant, the centroid is the center of mass, because you can pull the delta out and cancel it. And the book will call it center of gravity because it's assuming constant density, it's constant gravity all through. Suppose I did this, find the centroid of this region. I'm going to take the region below y equals x squared from x equals 0 to x equals 1. Wonder where that is. If I make this out of uniform material, this will be the balancing point, the center of gravity, same as we calculated before. If not, it still has a really neat property that's going to come up in the theorem. So the centroid has more significance than just agreeing with the center of mass for a constant density thing. It also has a wonderful geometric property for line coming up. So what is the centroid? We simply say x bar. It uses the same notation actually, which can be confusing. So the center of mass and the centroid use the same notation. For the centroid is the integral from 0 to 1, in this case, by 3, we'll say. Integral from 0 to 1 of the function x squared times x dx divided by the integral of the function without the x. Integral 0 to 1 x squared dx. Isn't that easy? Just integrate the function times x on top, integrate the function on the bottom, and that's it. So the centroid of this region is integral of x cubed is x to the 4th over 4. Put in 0, 1. Integral of x squared is x cubed over 3. Put in 0, 1. Well, let's see, it's 1/4 over 1/3 comes out to be 3/4. There's the centroid. You could put a, if this is a uniform material, you could put a little fulcrum right here at 3/4 and it would balance. The big weight on the right, close to the fulcrum, would be balanced by the littler weight on the left, sticking farther out, like the teeter-totter again. All this carries over to more dimensions. We're not going to do it in this section, but technically you can find a y bar, the balancing point in this direction. And then if you take x bar, y bar here, you can turn this thing over and balance it on your finger, the plane region like that, if you get both x bar and y bar. We aren't going to do that in this section. It is coming up later in the book. Okay, now the theorem of Pappus. This one's more fun, I think. It shows you the significance of the centroid. If a bounded plane region, bounded just means it doesn't go out to infinity anymore. You can fit it inside some circle of some finite radius, right? If a bounded plane region is revolved about a line it doesn't intersect, so it's on one side of the line, is how the book puts it. What do you think the volume is of the solid it generates? This is an arbitrary shaped plane region. How can I say something significant about the volume it generates if it's an arbitrary shape? Just lies on one side of the line. the volume generated in the solid by revolving it is V equals 2 pi R, I'm sorry, 2 pi X bar, let's call it, I guess, times A, where A equals the area of the plane region. So this assumes that it actually has an area, which is what we mean when we have a plane region. And what's the significance of this? And X bar is the centroid. Two pi X bar is the distance the centroid travels. And this is the area of the plane region. So that's a very significant geometrical quantity. You can take the area of the plane region and multiply by how far the centroid travels and figure out what's the volume of the solid generated. Ever see the Simpsons TV cartoon? I mean, it used to be hugely popular. Maybe it's getting old now. I don't know. Actually, some of the people in that show are frustrated mathematicians. If you Google something like math problem Simpsons, they'll come up with Homer Simpson supposedly solving some of the world famous math problems. It's very funny if you know the history behind it. He supposedly disproves Fermat's last theorem, for instance, which is famous. It was just not proved until the 1990s. Andrew Wiles came through with this immensely difficult proof for a very simple proposition. It's so hard that hardly anybody in the world can understand it, but they agree that he proved it. So, okay, I think he's out at Princeton now or something. But Homer Simpson puts up an example where he disproves it. And it almost works if you have a calculator without enough significant digits. So it looks like he's got it because the people who wrote The Simpsons are frustrated mathematicians and actually put together a good problem for him to put up there. And he has this other problem of topology. They say, here's the policeman's dilemma. Police officers are supposed to go to donut shops all the time, right? Topologically, two objects are classified by deforming them into a sphere with a handle, or a sphere with two handles, or three handles, but it's the number of handles that makes them equivalent. You want to be able to continuously deform closed surfaces into one of these things. And so the objects that all continuously deform into a sphere are in one category, and those into a sphere with a handle or another, two handles or another. And what you can show is that the donut, I mean, you can see it actually, right? And the coffee cup are actually topologically equivalent because you can continuously form this one into a sphere with a handle, right? The hole is right there. And so Homer Simpson actually eats his way to victory, if you see the cartoon, by eating his way through it till it's a circle. So he does things like that. Anyway, I got started on this because here's an immensely popular, important problem. The Homer Simpson is the volume of the donut, right? What is the volume of the donut? Suppose I take this circle over here of radius 2, and it's out here at x equals 3. And I revolve it around the y-axis, like that, to create a donut, right? Mathematically, we call it a torus. But when we revolve a circle around like that to make a donut shape. What is the volume of the torus if I take a circle of radius 2 out at x equals 3 and revolve it around? Well, what we said is it's 2 pi r, 2 pi x bar, the distance the centroid travels. What's the centroid on this circle? Here's the plane region that we're revolving, it's the circle, or the disk, actually. There's a stupid difference. I mean, the real picky things is you call the points out here along the edge of the circle, and the disk is the circle with its interior, or the open disk is the interior without the circle. Those kind of things, just to be pedantic in proofs. But if I take this disk and revolve it around a y-axis, what is the volume that's generated? Where's the centroid of the disk? Gives you symmetry. That's actually in some of the problems too. If you look at this one, you just say, where's the balancing point? When it's uniform density, it will balance, this half will cancel this half, and it will balance right here at this point here at x equals 3. So we notice by observation, x bar, the centroid is 3. And I revolve it around the y-axis at that radius. And now I call this formula 4. And let's see, x bar is 3, and the area of the disk is pi r squared, so it's pi times 2 squared is 4 pi. And so then we'll say by formula 4, the theorem of Pappus, the volume is 2 pi x bar, 3, area is 4. It's just 24 pi, and the calculation of the volume of the donut is easy as that. Now Homer Simpson knows how many calories he's got, right? It just multiplies still. After solving Fermat's last theorem, disproving Fermat's last theorem, and all those other heady, difficult problems. I'm sorry, I'm blocking on some of these, and I should move this. All right, I think I'll just leave that there. I gave you a couple problems on those. Oh, it's only 7 o'clock. Is that right? Maybe I can start the next section. And I thought I was going to finish about here. I was looking at the time a little while ago.
Why wouldn't the 4 have pi as the
Oh, good question. I forgot my pi there, didn't I? Yeah, it's 24 pi squared. Thank you. That's why you need to be here in class. I'll fool everybody online because they won't want to speak as much probably. Yeah, thank you. 24 pi squared. All right, well, I guess we'll go ahead and start the last section of the chapter then. This is probably the least important section of the chapter. Sometimes when I have not enough time, I'll skip this section for that reason. I almost just want to give the formula. But for people who are interested in fluid mechanics, it's slightly useful. But again, the purpose of it for mathematicians is just to get used to breaking up problems into little tiny pieces. And it's this fluid pressure and force, the submarine problem, if you will, right? You take something underwater, and this is kind of an interesting thing just to learn in this class. This is what makes you capable of dealing with issues when you get out in the workforce, right? Suppose I put this is supposed to look like it's horizontal here, a flat square down here. I can compute the pressure on it. Pressure is force per unit area. That's pressure. Consequently, force is pressure times area. You can write that back. And so I might ask, what is the pressure, pounds per square inch or something? Right? Pounds is a force. Square inches is an area, unit of area. I could say, what's the pound per square inch in this rectangle down here? Well, it turns out that what happens is water tries to conform on both sides, and the pressure in water is an incompressible fluid. If you take a balloon that's a foot radius out in the air and you take it down 100 feet underwater, it's still a foot radius, because what happens is it doesn't compress. It actually just pushes back harder and harder. It's got a lot of pressure underwater, but it's still the same radius balloon applies. And so what happens is that the pressure down here, because it's an incompressible fluid, is equal to, say that the pounds per square foot or whatever it is equal to the weight of the water sticking on top of it. So the force sticking on top of the rectangle divided by the area of the rectangle gives you the pressure for a horizontal object. For horizontal objects, at a depth h, let's say, make this h, the force F is equal to the density of the weight density of water as opposed to the mass density. Weight density gives you the force per cubic unit as opposed to mass density gives you the mass per cubic unit. So we need to get force. And it turns out it's 62.4 pounds per cubic foot is the weight density of water. Let's say in water, I should put here, at depth h. And that's the force. And then you divide it by the area. And if this is, well, let's just put it divided by A, where A is in square feet. I still put this as pounds on the top, I'm sorry. I'm not doing this right. Oh, I know what the trouble is. It's 62.4 pounds times the volume of the water sticking on top, which is A times H, which is square feet times feet is cubic feet. Well, this is pounds per cubic foot, sorry, times the cubic feet in water gives you the pounds of force on top of the sheet, and divided by the area in square feet. These cancel. There we go. And you've got 62.4 pounds per square foot. 64.24 divided by the area, pounds per square foot is the pressure. Whoops, should be pressure. I started at force. Pressure is the force on top divided by the area on the bottom. Gives pounds on the top and square feet on the bottom. There we go. And so it's easy for horizontal objects. You just take 62.4 divided by the area, and that gives you the pressure. But what if this thing is not horizontal in the water? What if instead it's vertical? For a vertical lamina, it doesn't have to be a rectangle. Let's just do the rectangle to be simple here. Length L times width W equals the area. Now what's the pressure? It's down below water, and some of it up at the top has one pressure because it's down a certain height. And the rest of it is down deeper, and so the pressure is varying as you get deeper and deeper. The pressure is actually proportional to how deep you are. You can see out of this actually. You're twice as deep as twice as much pressure, because there's twice as much water sitting on top of you. And that pressure is equal on the bottom and top, so that, I mean, the water on top pushes down against the water on the bottom, it pushes back, and so they're both pushing against each other with the weight of the water that's sitting on top of them. That way the water doesn't move. And so I've got a width and a length. How can I find that? Well, you can break this up into slabs. more generally, you might have some other shape object under the water, and you want to know what's the pressure on this one that's vertically submerged. And it's got different pressures at different depths. And what you can do is make an x-axis, and if you I think they measured it this way down for which way they measured this now. They just called it h of x, the depth here is what they did. All right, and so if rho is the density of the fluid, it doesn't have to be water, it could be some other incompressible fluid, or an object of this sort, break it into layers, each of which the pressure is approximately constant on. Of height, delta xk, and I should say break it into n layers, and width, f of x. Putting an x-axis down here. So you've got an x-axis, maybe like that. And you think of making little rectangles that look like this, that fill up the, and what you're doing is you're taking little, very thin rectangles, and each one has width delta xk at the kth one, and it has width f of xk star at the kth one. And so delta x times f of xk is the pressure on the kth piece. I'm sorry, the area of the kth piece on the kth piece. The area, AK, is f of xk star, the width at that point, times delta xk. I'm just deriving a formula here. Actually, I was just looking there for the notation. They use W for width. Let's call it W, just to be suggestive like they did. Width W of x. So there's the area of the kth piece, and then you multiply it by the density function. You get the mass of this. Let's see. Well, the way they did it, they used rho for density in this section. All right, and so the pressure on the kth piece is then approximately let's see, for density rho of the fluid. Is approximately the area times the height you are below the water. This gives you the mass of the water sitting on top of it, right? Area times height gives you the volume of water sitting over it. Times the density of the water gives you the mass of water sitting on top of it. I'm sorry, so this is the force, I guess I should say, the force on the cave piece. Is this, so it's the volume times the density gives you the force. The weight density. Gives you the weight of force. On the cave piece, Fk, then you add all those together. The total force is therefore you take F as the limit of the sum. If you sum these, you get an approximate force. This is the approximate force, I should say, on this one. Is the limit as the number of pieces goes to infinity of the sum k equals 1 to n of ak h of xk. I should say h of xk for the kth piece times rho. And ak is this, w of xk delta xk. So this is limit n goes to infinity of the sum k equals 1 to n, ak, w of xk star, let's put a star on here, h of xk star, rho delta xk. There it is. But that's just an integral. And we'll say, therefore, the force on the object at a depth, at a varying depth, is the integral, by rewriting this as an integral, w of x, I just replace the xk stars with x's, h of x, rho, I can put the rho up here, delta x. There it is. It's just the width of the object times its depth, h below the water, gives you the area of water sitting over it, times the density gives you the force of the water. So this is the infinitesimal force of the water sitting over the small piece, and then integrating from x and a to b. There's the formula, we call that 5. And next time what we'll do is a problem similar to this. All it has in this section is this one formula. It's just supposed to show you how you can break this up into pieces. When you have a submerged object, you can take a whole bunch of rectangles, add up the force on each one, and get the total force pushing on this thing underwater. Then you divide it by the area, you get the total pressure on there. So let's leave that like that for now. And here's the problems I'd like to do about out of 5.7 on centroid, center of mass, and the theorem of Pappus. Look at 1 to 21, every other odd. So this is only like 6 problems. The first ones are center of mass. I think the last ones are centroid. And then 36 and 38 are the theorem of Pappus. Then we'll do a couple of pressure problems next time. It won't take long at that at all. It's just, once you have the formula, you plug it in. And we'll charge on to the next chapter. How about that? All right. Well, see everybody Wednesday next week. There's no class on Monday.
Thanks, sir.